Hello everyone, and welcome to today's broadcast. Today is Tuesday, August 4, 2026. I'm your host, Nino, and I am super excited to be here with you today. We have a really fun atmosphere going on here, and I hope you're all feeling as laid back and ready to learn as I am. I am introducing something that really caught my eye. It is about robots, reinforcement learning, and how we can make machines understand the world a bit more like we do. But before we dive into it deep, let me tell you a little joke. Why did the robot go to the therapist? Because it had too many partially observable Markov decision processes. Oh, I guess that one is a bit too niche. Anyway, let us get right into the meat of today's topic. The title is OpenMOSSWCM World Critic Model for Vision Language Action Reinforcement Learning. The draw is Cheats, Dowson. Orig codes in 607,29,631. It is long. So what is this paper all about? You imagine you are trying to teach a robot how to fold a towel. I'll pick up a piece of sushi from my moving conveyor belt. In the past, researchers used something called Vision Language Action Models, or flaw models. These are essentially big AI brains that take in visual information, like what the robot sees through its cameras. Combine it with language instructions, like when you tell it to pick up the sushi. And then output the physical actions the robot needs to take. Traditionally, these models were trained by watching humans do things, which is called supervised fine-tuning. But there is a catch. If the robot encounters a situation it has never seen before, it gets confused and fails. To fix this, researchers started using reinforcement learning. This is basically a system of trial and error, where the robot gets points for doing a good job. In reinforcement learning, there is often a component called a critic. The critic looks at the current situation, or state, and tries to predict how valuable it is, meaning how likely it is to lead to a successful outcome. But here is the massive problem that this paper is trying to solve. These critic models usually only look at a single frame of video, like a photograph, to make their judgments. Imagine trying to figure out if a baseball is going to hit a window just by looking at a still photograph of the ball in midair. You cannot tell how fast it is moving, or in what direction. You are missing the dynamic information. In technical terms, robotic control is a partially observable Markov decision process, meaning one snapshot does not give you the whole picture of the world. Some researchers tried to fix this by just stacking multiple frames together, like feeding the critic a short video clip instead of a photo. But the paper points out that this still fails, because simply guessing a score based on a sequence of images is not enough supervision for AI to truly understand how the world works. The AI does not really learn the physics or the dynamics of the environment. This is where our hero, the World Critic Model, OpenMOSSWCM, comes in. The researchers decided that the critic should not just estimate a score, but it should also try to predict the future. Yes, you heard that right. The OpenMOSSWCM is built on an architecture that jointly predicts the future latent state of the environment and estimates the value. By forcing the critic to imagine what is going to happen next, it learns to capture the temporal dynamics of the world, rather than just guessing a number. Let us compare this with other technologies. Older critic models are like a person trying to navigate a maze by only looking down at their feet. They might where they are right now, but they have no context. Even the slightly newer models that look at a few frames are like someone looking at a flickbook and not understanding the story. On the other hand, is like someone who watches the scene, understands the laws of physics, and can anticipate the next move. The paper shows that when they tested this on 139 different tasks and simulation, the OpenMOSSWCM consistently beat the state-of-the-art models. For example, in one test, a model starting with a near zero success rate jumped up by 12,551% after training with this new method. That is just bonkers. Now let us talk about how this applies to everyday life. Because I know we're all wondering when your robot is going to come do your chores. I have got 3 specific application examples for you. Let's let us think about Hoini. The paper explicitly mentions tasks like folding a towel and cleaning a stovetop. Right now, robot vacuums are great at driving around in circles. I imagine because the WAM allows the robot to understand the dynamic flow of objects. It can handle squishy or flexible things, like a crumpled shirt on the floor. It knows that if it pulls one sleeve, the rest of the shirt will follow in a certain way. This technology could finally bring us the ultimate robotic housekeeper, saving us countless hours of tedious labor. Second, think about the food service industry and dynamic manufacturing. One of the real-world tasks they tested was picking up a piece of sushi from a moving conveyor belt. This is incredibly hard for older robots, because the object is constantly moving out of its field of view. With the World Critic Model, the robot anticipates where the sushi will be in the next second, allowing it to smoothly swoop in and grab it without knocking over the soy sauce. This could revolutionize factory assembly lines, sorting facilities, and even automated restaurants, making them much faster and more reliable. Third, consider assistive robotics for the elderly or disabled. If a robot is helping someone with mobility issues, it needs to be incredibly safe and predictable. If it is handing a glass of water to a person, it needs to anticipate the person's cell movements to avoid spilling, because the wine trains the robot to predict future states and understand complex dynamics. It can interact much more smoothly and safely with human beings. It will not just blindly execute a motion, but will constantly update its internal world model to ensure gentle and successful interaction. It is really fascinating stuff, is not it? The idea that we're teaching machines not just to see, but to imagine the immediate future, makes them so much more capable. And the fact that they tested this on real physical robots, like the Wodarch 250s, and it worked beautifully with very little training data, is just mind-blowing. Well, that is about all the time we have for today's deep dive. I hope you enjoyed this journey into the mind of a robotic critic. I'm Noah, and I will be back next time with another awesome paper from the archives. Stay curious, my friends, and keep looking towards the future. Catch you on the flip side.